In today's video, we're going to look at how electromagnetic waves behave when they run into a boundary. And to start this discussion, let me remind you how regular waves, mechanical waves, behave when they hit the boundary. So we actually saw this earlier in the semester. If I have a mechanical wave traveling along in some medium, so the blue line represents my medium, and this red line I'm drawing right now represents a hard boundary of some kind that the wave is going to run into. What you'll remember is that when the wave hits a boundary, it's going to reflect back in the direction it came, but it's going to be reflected like this. So it's going to be flipped over, and it's going to move backwards in this direction. Light does kind of the same thing, and you guys know that because at some point in your lives you have looked in a mirror. So what is a mirror but a hard boundary for light to reflect off? So if I draw this black line here, and I call that the mirror, then let me imagine I have a light wave heading towards it. When I talk about light waves, though, I'm not going to draw sort of sinusoidal waves like this. What I'm going to do is come up with this mathematical convenience, which is a ray of light, a so-called ray. And what is a ray? It's like you take part of a light wave. If you're a kindergartner and you're drawing the sun, you would draw like little rays coming out like this. I think some adults might do that too. Note some earlier videos. So what I'm going to do is I'm going to imagine my light wave is a straight line, and I'm going to draw that straight line of light right at the mirror. What's that straight line going to do when it hits the mirror? I feel like you all know it's going to reflect back in exactly the opposite direction. The question is, what do I mean by the opposite direction? It would be very reasonable to say, well, okay, the opposite direction means that this angle right here, the angle at which it came in, I'll call that theta 1, is equal to this angle right here at which it comes out, I'll call that theta 2. And that is absolutely true, but it's not how we measure it. And the reason why it's not how we measure it is, well, let's think for a second, what would be different if our mirror was curved? So if the mirror is curved, the light is going to do exactly what you'd expect it to. So if this is my ray of light, and it comes, it hits the mirror, and it bounces off just as you would expect it to. But the thing is, I can't really measure these angles anymore, the ones that I called theta 1 and theta 2 in the other description. Like this angle I called theta 1 and this angle I called theta 2. You can't measure those, and the reason why is because you can't measure an angle between a straight line and a curved line. So what we're going to do is we're going to exploit this idea that we talked about in the fall, where we talked about the normal to a surface. So if I just look at the mirror, if I zoom in a little bit at the point where it hits, and at the curved surface, I'm going to try and draw a line that is perfectly tangent to the circle at that point. So here's my line, it's pretty much tangent, and what I expect is that the light should reflect back off. So instead of measuring the angle from the surface, what I'm going to do in the case of a curved mirror, and in fact what I'm going to do in the case of any kind of mirror, is I'm going to draw a so-called normal line, which is a line that's perpendicular to the tangent, or perpendicular to the surface at that instant. So this line is at 90 degrees, this dotted line I just drew. That's a 90-degree angle from the tangent line, and now what I can see is that my incident ray, theta incident, and my reflected ray, okay, those were supposed to be the same angle, everybody. Okay, theta I is supposed to be equal to theta R. So sorry, they aren't, I know. So the incident angle and the reflected angle are equal to each other, and we call that the law of reflection. It's kind of obvious, but here we go. We do always define the angle from the normal, from that dotted black line, and we never define the angle from the surface, just because of that curved mirror incident. Okay, let's look at two cases of reflection. One is called specular reflection, or we We usually just call that one reflection, and that's when you have a flat surface. So this yellow ball I just drew is my light source. So here are my imaginary rays of light going off in all directions. So those rays of light are going to go off in all directions and hit that surface, and then they're going to bounce back according to the law of reflection. So a ray of light in this direction will bounce back like this. A ray of light in that direction will bounce back like that. So incident ray, reflected ray. And that's when I have a very flat, smooth surface. So what you guys might notice is that if I take any of these reflected rays of light, and which rays are the reflected ones, so this is a reflected ray, 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 and I trace those reflected rays back behind the mirror, well, let me trace them back. Here's a reflected ray, I'm tracing it back. Notice as I'm tracing these backwards, I'm making dotted lines. What you're going to notice if you did your drawing pretty accurately is that those reflected rays meet up at a point on the other side. And that point on the other side is called the image of our light source, which I can also call the object. So if you have a nice, flat, clean surface like a mirror, you're going to get a clear image. A couple things that you might notice about the image is that it's on the opposite side of the mirror from your object. It's about the same distance. In fact, it's exactly the same distance from the mirror as the object was. So if I call this the object distance dO and the image distance dI, then my object distance dO is equal to my image distance dI. So the reason I'm able to form an image is because any reflected ray is going to hit an angle, is going to hit sort of the same normal. So it's always going to come back and reflect that way. And you guys are going to do an exercise later where you show that you can get an image for specular or regular reflection. Let's just look for a second at what's called diffuse reflection though. This is also very common, although not really as useful. So again, here's my light source, my little sun, and my rays of light are going off in all directions, just as my rays of light were in the other drawing. But because the surface here is highly irregular, and if I zoom in, you can see how irregular it is. When, let's say, this ray of light gets to right here, my normal would be up straight, more or less. So this one would reflect more or less the way you would expect. But this one, though, if I look at some of the other ones, this one, my normal is going to be off slightly at a different angle. So it's not going to reflect quite as well as I would expect. And then for some of the other ones, like this guy, I realize it doesn't help that much to zoom in if you have such an irregular picture anyway. It's going to reflect more or less back directly the way it came. And this one too, it's going to have a normal that's kind of off like this. So what's going to happen with all these irregular reflections bouncing off an irregular surface is that if I trace the reflected rays back and make a so-called virtual ray, these don't meet up. Like this one is just going off somewhere, and if I look at some really weird ray, like let's say this one's going to bounce back more or less like this, and my reflected ray is just going to be there. So they're not going to meet at a point. They're not going to form an image. So diffuse reflection, you're not going to be able to get a clear location of an image. Couple of examples of when you see this, specular reflection, irregular reflection, that's what happens when you look in the mirror. If you imagine that this little sun I drew here was in fact your happy face, then you in the mirror are going to see yourself on the opposite side of the mirror, the same distance from the mirror. You might say that you see yourself behind the mirror. That's very common notation. But let's say you're looking at the rays of light that are bouncing off you and hitting something that's not flat, like a wall or a hard ground or something. The light that's bouncing from you to the ground is still going to bounce back, but it's not going to form an image because the reflection just can be all over the place. So think about it like a pool of water. If the pool of water is perfectly smooth and flat, you can see yourself, you can see your reflection in that. But if you drop a stone in the water or they're about to wave, you are no longer going to get a reflection. So there are some of your ideas about the law of reflection. As you guys do the exercises I left for you, there's actually no math in this, but there's a lot of measurement. Make sure you get a protractor. The substitute has protractors. Make sure you draw things accurately. Draw a normal, measure your angles carefully. Okay, have fun, guys.